All right, hello. My name is Oleg Zhurakousky. I represent Hortonworks, a Hadoop big data company you might have heard of. So, and today we're going to be talking about some of the recent things that I've been working on within Hortonworks. Can everybody hear me okay? Yes, good. All right, so I only have 30 minutes, and what I'm about to present will probably take much longer to dive into all of the details. The good thing is that I'll be doing a user group meeting tomorrow where we're going to be having a lot more time to discuss and dive into the details. So what I'm going to be talking about, I'm kind of primarily summarize and hit on the most interesting topics, but unfortunately I won't be able to cover everything that I would like to cover within 30 minutes. So, and of course, if you guys have any questions, don't necessarily wait till the very end. Raise your hand and let's tackle it right away. Okay? So I'd like to begin with this slide and kind of ask you a rhetorical question. If I were to ask every single person in the room, what is big data? What are the chances that we would all come up with the same answer? Probably slim to none. Right? So it's yet another buzzword in the industry, and it means a lot of different things to a lot of different people. So I kind of want to try to define what it means to me. So again, I work for a Hadoop company, so the obvious answer, if the data is in Hadoop, if it's a lot of it, then it's a big data. Well, it's not necessarily true, because we definitely cannot judge big data by its size, right? Because if I ask you, is 1 gigabyte a big data? Well, the answer is, again, it's relative. If you want to process this 1 gigabyte in 1 nanosecond, then yes, it is big data. But if you want to do something within 3-4 seconds on a decent laptop, then no, it's not a big data. The same goes for terabytes, zettabytes, and everything else. So what big data means to me is actually the global data, right? So yes, within Hortonworks, within Hadoop ecosystem, we kind of trying to advocate bring the data into Hadoop, and there's many different arguments why one would want to do that. But the reality is, to even bring this data into Hadoop, you need to get this data from somewhere. That could be sensors, that could be Twitters, that could be your social media, could be RDBMSs. You try to offload the data that cannot fit there anymore, and so on and so forth. So the big data is, to me, is just the data everywhere, right? That creates a very interesting problem. So I'm going to assume that everybody here is Java developers, because this is kind of a Java-centric. We're going to be looking at some code as well. So, and if you think about the actual big data in terms of processing, we have a lot of different problems that we need to solve as developers, right? So first of all, many sources in many forms. What does that mean? So if you're trying to read a file, for example, you have a variety of things to deal with: input streams, buffered readers, and things of that nature. Or you can process. You may have some collections, either arrays or real collections. And then if you start talking about things like Facebook, Twitter, and various different social media and sensors, then each one of those will either come with its own API, or you have to figure out the way how to actually extract the data from it. So, but the interesting thing is that once you figure out how to actually get the data from it, the data kind of comes to you in the form of iterable of elements that needs to go through some type of computation. That's the typical process that we do. So we have a file, we're reading, we're trying to find something in it, or we're trying to actually put this file into a structure that we can load it into RDBMS or into Hive, which is the Hadoop sort of a database, so to speak. So we need to do some type of processing on that data. And because we source the data from a variety of different or we source the data in a variety of different forms, we kind of have to start be very proficient in how to do the same task within the context of a particular API. I want to kind of quickly switch to just a very trivial example. So here's an example of, we're trying to read a file, right? So now we chose buffered reader, and we got our single line at a time, and we're spinning in a loop trying to do something, right? Here's the same example. We're doing the same thing, but the data actually comes from JDBC, from database, right? After we execute the query, we got some result set, and we're still trying to process that sequence. The same goes if we try to parse a string, and that's an example of saying, okay, well, now we have an array, and we're back into creating our own custom loops and creating our own process how we want to do that. Efficiency of the computation, basically what you're going to perform within that loop, actually depends on your skill, right? Because there's a lot of sort of there is no consistency. There's a lot of boilerplate code that you would have to do. For example, I'm going to switch to another example. Here's the I just written it kind of 10 minutes ago. Don't have to try to understand what's happening here. This is basically the classic word count on a file that contains basically records, right? So we're basically creating a file, we're spinning in a loop line at a time, then we're splitting it into the words, and then we're kind of adding it into the map and so on and so forth, right? So if you think about, and there's another example that I'm going to be showing later with the JAVA8 streams and how much more efficient that is, but we'll skip it right now. So again, a lot of a boilerplate code here that we as the developers try to avoid if we can, and a lot of times rely on a variety of frameworks to do so. So, and obvious issues of integration. Again, if you let's say pulling data from Twitter, you're pulling data from LinkedIn, or you're pulling data from a variety of sensors and so on, you have to be proficient in how to get the data and also be proficient in how to process this data. So a lot of times the specific abstractions kind of leak into your code. So if you think about it, when you process the data, let's say it comes to you as iterable of strings, right? Then the code, the processing, the computation code, should be the same regardless whether that string came from Twitter, or whether that string came from sensor, or whether that string came from log file, right? But now because you have to rely on one or the other API, then inadvertently those abstractions may leak into your code. So if you eventually want to transfer that process and apply it to a different source of data, you realize that you can't just do it because you kind of locked into a specific API. So, and again, there's no unified programming language. We have a variety of them, right? And we have a variety of frameworks: Spark, Test, Flink, Cascading, Scalding, and there's many more to mention. So, and a lot of them bring in new concepts and abstractions, like, anybody use Spark? Flink? All right. So, for example, in Spark, they have a concept of RDD. In Flink, they have a data set. And then in Tez, we have processors, readers, and writers, right? So you kind of have to become familiar with the underlying system to where all you care about is to actually build a, sort of an execution pipeline to process a specific type of data and transfer it, I mean, not transfer it, transform it into the form that you would like to do sort of the final form, right? And on top of that, there is a different execution paradigm. So when you're talking about big data, one of the big difference in terms of processing big data in Hadoop-like environments is a different paradigm in terms of processing. We're not looking at the big data kind of like from the storage perspective. Actually, it's kind of the opposite. We bring the code to data because the data is naturally distributed and execute it right where the data is instead of bringing it over the network to a single processing kind of environment. And then there's different deployment models. So, and because of some leaky abstractions, a lot of times, not only you lock to the abstractions, you actually lock to specific execution environments. For example, with Spark, we try to convince Spark community to kind of separate their execution model from their API. They were not very receptive of that. So, for example, today in Spark, I mean, Spark does integrate with a variety of resource managers and so on, but Spark will not allow you to plug in your own execution environment. So, and there's a lot of cases where this would be advisable or better than, for example, in terms of performance than Spark for certain specific use cases. But anyway, so developers essentially must become increasingly aware of the world around them to be efficient in processing big data. So, and again, I came, before Hortonworks, I worked for Spring, and you know, you kind of get infected with this mentality of separating the what versus the how versus the where, right? So when I code, I want to change heads. If I'm doing some system functionality, if I'm coding for that, then I want to put that head on. But if I'm coding something that comes to me as a part of a functional use cases and I'm putting a head of application developer, I really, really, really don't want to worry about the where and the how. I just want to worry about the what I wanted to do. So, and we'll get to that in a minute. So it's all about separation of concerns. So Java 8, finally we're in Java 8. So what is so important about Java 8 versus, let's say, Java 7 or 6? So Java 8 came with, it's as if they should have just make it Java 2 right off the bat, because it came with a lot of new language features. One of them is, well, features and abstractions, right? The feature would be lambdas, so now you no longer have to deal with anonymous inner classes, right? And there's actually a benefit to that, not just syntactic benefit, but actually runtime benefit, because it no longer relies on generating the class. It relies on invoke dynamic instruction, right? And the other one is not a language feature, actually a new abstraction called stream. And what stream, basically the thing in green is basically from the Java doc of the stream interface. It's a sequence of elements to support sequential and parallel aggregate operations. So it gives you this monadic style computation model over iterable source. And it consists of, the whole programming paradigm consists of 3 stages. The stream sourcing, and there's many different factory classes to define a stream from a variety of sources, and you can write your own, because you can easily create stream from any iterator. Then there's a computational pipeline composition. This is where you express what you want to do. And then there's an execution, basically the triggering of that pipeline for its execution. So if you think about it, it's kind of and we're going to see example in a second, but it's kind of the good old builder pattern, where we doing flat map, filter, flat map, and so on. We keep assembling the pipeline, and then each operation that you invoke returns you a new instance of stream, and essentially creates a pipeline that eventually you're going to execute, where all of the functionality that you expressed is going to be performed. So it is similar to collection, but it's not, right? Because if you think about collections were optimized for efficient data access, right? Where stream describes the computation which will be performed in aggregate. So in other words, you sometimes not even aware, because it depends on the implementation of the stream, how your loop will be constructed or how the computation will actually happen. And because stream is an interface, you can actually change. For example, you may say, I don't want to process one record at a time, I want to do micro batching. So you can actually do that within your implementation of stream. So the default reference implementation is called reference pipeline, doesn't do that, but nothing should stop you from doing that. So stream API consists of intermediate operations and terminal operations. So intermediate operations is the one that I told you that kind of resemble the builder pattern, which is they're lazy. By executing that operation, nothing will happen other than you're going to get a new reference to the stream that already contains that operation. So it's like an assembler. Okay? So flat map, filter is just a few examples of the intermediate operations. And then we have terminal operations, which essentially trigger the execution of that stream. So let's look at the demo of stream and specifically in relation to the word count that's written right here. So again, I can't even fit it on a full screen with the font size that I have here. But here's the same example, does the same thing, but uses Java 8 streams. So first of all, it's much less code to write. We all like that. But most importantly, it's consistent, and it kind of naturally allows me to understand what exactly is going to happen here. Because if you look at this example, I have to really read every line to actually understand, yeah, it's not a complicated code, but at the same time, I still have to figure out what it's doing. Now, because it's so verbose, we can argue that this code would be written a little more efficiently. So again, if I were to task everybody in this room to write this code without using JAVA8 streams, again, we would probably end up with the same result, but with many different implementations and many different coding styles, where if I ask you to write this code using JAVA8 streams, there's a good chance that majority of us, if not all of us, would come up with the same code, because a lot of the boilerplate is hidden. So if we look at this, we don't have to worry about how the map is going to be created. We're just simply relying on something that's already provided by the API itself, right? And we know the contract within the flat map function and operation that it will return a stream, which essentially where the parsing will occur. And now internally, it will also generate the loop and will be spitting out individual tokens as opposed to the entire array and so on and so forth. So now we're kind of having the separation between what we wanted to do and how we want to do it. Okay? So now it seems like Stream is a good API to kind of start living in the world of distributed data. Well, and that's what I started looking about 6 months ago, and realized that while initial view into this kind of, yeah, we can provide a variety of different implementation on top of Stream, the reality is really not there yet, or probably better say, it shouldn't be that way, because Stream was designed. I actually spoke with one of the guys who was kind of from Oracle, who was in the team who were working on streams, and his response was that JAVA8 streams were designed for the data. The actual reference implementation and API was designed for the data, which is like one cache miss away. In other words, if it's not in your memory, then it's probably right here on the disk. So when you're trying to look at the stream in the context of a distributed data, then things become a little hairy, and here's why. So first of all, not enough factory methods. So for example, if you want to go into the Hadoop, then you have to come up with your own factory to generate stream from it, right? Well, factories will be very easy to create, but the fact, how do you bring that code to data, right? You don't just want to bring stream, because you can easily create a factory to pull the data from HDFS and process it locally, but that's not what you wanted to do, right? Operations. So some operations have this impedance mismatch because, for example, if you look at something like stream count, it doesn't really matter whether you have a gigabyte or a zettabyte of data. At the end of the day, it returns you a single value of type long, which is, even if you have to transfer that over the network, that's only 8 bytes, right? Not a big deal. But what if you look at stream.collect? Collect returns you an in-memory structure. So what if you're collecting a stream that will essentially, because it's spread out across multiple, thousands of nodes in a Hadoop cluster, what if you're trying to collect it? You're collecting it here locally into a JVM space, right? So what's going to happen? Pretty quickly, you're going to get into out of memory, okay? And then serialization. So lambdas, by default, that's the equivalent of functions in Scala. Lambdas, by default, are not serializable. Any guess why? It's the same as with the web and SQL. We don't want to be able to transfer lambdas and inject code. So in other words, they're by default not serializable. But because Java multi-bound casting, you can actually do that, right? But again, you can do it doing something like this. Cast it to runnable and serializable, right? But can you imagine how ugly your code will look if you have to cast every lambda? And again, this one is a simple one, but what if you have really complex piece of code that within your function and you have to actually cast that? So again, it's not really a pretty code. So, and there's more. I just want to kind of stop on these three. And they're all mutually exclusive. In other words, addressing one will not solve the other one. So, and this is where I come up with this notion of a D-stream. So D-stream is distributable, not distributed. That's the important notion. So the data itself could be distributed. So basically you have this one unified API which you can process the local stream and then process distributable streams, and your code will never change. The reason why it's important is because I came from application development, so I know that while I'm designing something, while I'm playing with a concept or with an idea, I'm most likely dealing with some local files, with some local data. But what I want to make sure is that once I'm settled on the approach, my code that expresses functional requirement does not change if I try to apply this code within a distributable data environment, within distributed data. So, so that's why it's distributable streams, not distributed streams. Now, it's a higher level computation API based on Java Streams API. So it's not a replacement of Java Streams, it's actually distributing, and when we look at the architecture, it's actually distributing your Streams code, allows you to, sorry, not distributing, it allows you to build processes that will distribute your Stream code across whatever cluster you're running, whether it's a Hadoop cluster, Spark cluster, and what have you. So it builds stream-based execution graph, and it is execution environment agnostic. So it's not specific to Hadoop, it's not specific to Spark. Basically, there is already plugins exist to run it on Hadoop, run it on Spark, and so on, and you can implement your own to run it on your own custom execution environment, whether it's distributed or not distributed. So again, the goal is single API, multiple execution models. So primary focus to provide stream-based unified programming model to build ETL-style distributable data processes to be executed in a compatible execution environment. So that's kind of the definition. And the important part is also that the core API, and I'm trying to keep it that way, is extremely small. Basically, the core API has no other dependencies than Java. So there's no, I mean, if you look at the core API and it's Maven or whatever build system you're using, you'll see there's actually one dependency on JUnit. I like to test my code, but it's a test dependency. So it's an open source project right now. It's kind of a research effort, so it's not a fully fledged project. We're still kind of researching the idea and collecting the feedback, but it's getting some traction and people already started to use it. So here's quickly about architecture. As I said, the architecture is very simple. It's not replacing or re-implementing Stream API. It simply creates, and again, I'm going to skip some of the details, but we can discuss them tomorrow. It creates a dstream execution graph, right? So when you look at the code, and well, actually, I'll show you the code in a second. So it creates an execution graph, which is basically, if you're familiar with the concept of AST, abstract syntax tree, so that's essentially what the execution graph is. It creates a syntax tree which is sent to a dstream execution delegate, and dstream execution delegate is basically one of the core strategy where you provide which delegates to a specific execution environment. So for example, currently, dstream provides execution integration with Apache Test, which is the kind of evolution of MapReduce execution environment. So you can run it on Hadoop. It also integrates with Spark, it integrates with SQL, and it integrates with Apache NiFi, which is kind of a different discussion altogether. But the point is that you can, and also provides a local execution environment. So you can, again, start playing with your code, and I'll show you in a second. You start playing with your code in a local execution environment, and then simply change the execution delegate, and that same code will execute in distributed execution environment without any changes. dstream, from the API perspective, inherits a lot of the stream operations, so you don't have to kind of relearn, right? So basically, all operations that are compatible that don't fall into the category of that impedance mismatch are all kind of inherited from the streams, but the ones that are not are either changed or not even present because they don't make, for example, they don't make any sense within the concept of a distributable data, or I don't know yet how to handle it within the concept of a distributable data. Okay, and then there's also additional or modified operations. For example, we saw the collect, right? Collect is changed to reduce values or aggregate values. There's two different distinctions for that, right? But then there's new operations such as join, union, and classify, which again, we'll probably won't have time to cover today. So the reason, one of the goals, as I said before, is to make sure that you have this unified API while multiple execution environments, right? One of the ways that we've accomplished that is kind of separating certain configuration concepts from the API itself. So in other words, if you look at this is a kind of a simple configuration of, again, a simple word count, you can see that while you're creating a stream, and we'll actually might as well switch to the code. So we saw the stream code right now, and here's the code for using dstream. So as you can see, the code looks practically identical, right? The only difference here is in the factory method. Let me just switch to a new line. So I'm creating a dstream of type string. So essentially, I'm declaring to the developer, or the developer declares to themselves that they're going to create a stream where each element within a dstream is going to be of type string, right? But we don't know where the source is coming from because that's configurable. You can go and change where the source is coming from, whether it's a URI or a streaming source. You can change also through the delegate who is going to execute. For example, if you look at configuration, you declare from the delegate who is going to execute your stream. And again, it's a properties file. The reason being is because kind of a pro and con for that. So the reason being is that because I don't want to create multiple configurations for a variety of different things, so property file is the most natural thing where I can include whatever the framework configurations that are required there, but if you're trying to implement something of your own, you can still include them in the same properties file, and we can kind of share the same configuration. So basically you create a stream, and then you apply the same functionality. And in this case, as you can see, the big difference here is instead of collect, I'm calling reduce values. But if you reduce values is basically a streaming way of doing the same thing as I was doing here when I was doing collect, right? But in this case, I'm not asking to return, because collect is one of the terminal operations. I'm not asking to return me a map. I'm saying reduce values, which will be computed obviously into some type of a key value pairs, but most likely in distributed environments, it may end up in the file system as a key value pairs, right? And you don't, in fact, collect, there's another problem. Collect tells me that I want this data right away. Well, here, you're basically saying, I want this data to be executed. If I want this data to be brought into the collection or into the map or somehow, some kind of a structure, I will request it. But for now, all I'm saying is that compute this data, and then the execution environment you're running on is going to know how to store it, where to store it, because it's all part of the implementation of that delegate, right? So now we only have one terminal method called execute as, which returns you a future of stream, and that is because, again, one of the aspects in distributable environments is that your result often is written to a file system or into some type of distributed memory in the form of partitions, right? So it gives you a stream into partitions. So now when you, for example, if I try to run it, you can see that I have a utility class that prints me which partition it's coming from. So I can see the same word count, but it prints to me that this comes from this partition, this comes from that partition, and so on. So again, you can look at it as a single view, or you can look at it sort of in a partition view. Okay, that's kind of good presentation. So so we got to the demos. So actually, I did pretty good on time. So quickly, any questions, guys? All right, so just to summarize it, again, it's there's going to be a more detailed discussion because, again, I'm showing you the word count example because it's the most trivial. So currently there's support for pretty complicated joins and unions, and in fact, here's one example that I have time to run, which is basically does something that if you ever work with in a Hadoop environment and try to do it yourself, it's actually a pretty complicated process. For example, joining the data from relational store and unstructured data. So in this case, it could be Hive or it could be basically RDBMS in a totally different system. So here's an example where I'm actually performing a join between two separate sources, where one source comes from a relational database. This is just a test case. It uses Derby. And another one is unstructured file, right? So if I run it, so, and here's my join, right? So the data was joined, and again, it only took me 3-4 lines of code to accomplish. So, like I said, even though the project is still in its kind of infancy and still considered to be a research effort, there's a lot of functionality that's already available. There's already some community contributions and following. So. Here's kind of what's in the roadmap, integration with variety of data sources, integration with variety of execution engines, so Apache Test, NiFi, Spark support's already provided. In fact, so again, I can run it, but as you can see from the code, this is my Spark IDE or Scala IDE. Again, the same code, but running in Spark execution environment, so nothing changes on the configuration. Right, so from a developer perspective, it gives you that kind of a warm and fuzzy that You can write this code once and then hopefully run it anywhere. So streaming, so it's kind of a name collision, but streaming, like a conventional streaming, where we want to be able to stream the data in from, let's say, a socket or some kind of like a Twitter fire hose or something. So that's coming, and then support for multiple file formats. Right now, I'm only dealing with the text files and sequence files, but that's a sequence file. That's a Hadoop guys would know what it is. Non-Hadoop guys, it's basically a key value file in Hadoop. But ORC, that's a columnar-oriented file within Hadoop ecosystem, Avro, and many different file formats. And real-time reporting, which is ability to, well, these jobs in distributable data environment tend to run sometimes long time, so sometimes you want to be able to have some real-time reporting, whether it's a statuses or you just wanted to get some information about interim results. So that's coming in the horizon. So again, project is open sourced, Apache license. Anybody can access it, so you can find it in Hortonworks dstream, or you can just go to dstream.io and it will link you to the same GitHub repository. And I'm done. Thank you so much. If you guys have any questions, I'll be here, so thank you.